combustion simulation approaches, DNS, LES, and RANS, and that RANS and LES require models for turbulence, chemistry, and transport. DNS is used to glean understanding, fundamental mechanistic understanding. It's also used to develop and test models, both in an a priori as well as in an a posteriori sense. A priori meaning that you get information for the statistics from your model and compare it with those from the DNS. A posteriori meaning that you include the models in your RANS or your LES and then combine the numerics as well as the physical models and compare statistics, means, and variances against the DNS. DNS, as I mentioned already, resolves all scales, but it's not free of modeling entirely because we still need to have models representing both the chemistry as well as the molecular transport. I'd like to quickly go over some of the underlying mathematical formulation for the equations that we solve, and then some comments about high-performance computing. So I've already shown you this plot here, and as I said, we're focused mostly on DNS in this work, and resolving now on machines like Summit at the Oak Ridge National Laboratories, on their Summit supercomputer, which is a 200 petaflop machine. So it's 5 times smaller than an exaflop, which is where we're targeting in 2021. Exaflop is 10 to the 18 floating point operations per second. And so we can get about 5 decades of scales directly resolved using DNS on those types of machines. The governing equations that we solve for example, in a compressible solver that I've written, it includes the conservation equations for mass, for density, momentum in 3 directions, the total energy, and the species continuity equations, conserving the species, where the, the total energy here is the sum of the internal energy, shown here, and the internal energy on the right, these right 2 terms, and the kinetic energy shown here. And then you could have additional body force terms on here. We solve in the momentum equation. There's a constitutive model for the stress tensor. See tau beta alpha. And if you have any body forces, you can add, like buoyancy and so on, you can add them. F alpha I is the body force. And then Q beta in the energy equation is the heat flux, represents the heat flux vector. And the V beta alpha also in the energy equation is the species mass diffusion velocity. Omega dot in these equations for the species continuity and the energy represent the molar production rate of species I, and E naught, as I mentioned earlier, is the specific total energy. By the way, these equations are provided in the article referenced below, as well as in many textbooks by Poinsot and Vignant, and also by Foreman Williams, if you want to get a more detailed reference of these. Some of the constraints here are that conservation of mass, the sum of the mass fractions has across all species has to sum to unity. We typically deal with an ideal gas, perfect gas mixture, where the equation of state pressure is related to density temperature through the mixture molecular weight. And the species mass fractions, yi, and the mole fractions xi are related by the species molecular weights, the ratio of that to the mixture molecular weight. And then below here, I've got written some of the relevant thermodynamic relations between enthalpy and temperature for an ideal gas mixture, where the mixture enthalpy is the sum of the species enthalpies weighted by their mass fractions. And the species enthalpies have both a sensible as well as a chemical component. The specific heat at constant pressure of the mixture is the sum of the individual species specific heats, again weighted by their species mass fractions and summed over all species. And the difference between the isochoric and the isobaric specific heat is the ratio of the gas constant to the mean mixture molecular weight. There are a number of constitutive relations that enter these equations. As I mentioned before, there's the viscous stress tensor, shown by tau beta alpha, the species diffusion velocities, V sub alpha I, and the heat flux vector, the Q vector in the third equation, equation 12, where mu is the mixture viscosity, kappa here is the bulk viscosity, and then the dij's are the multi-component diffusion coefficients. D sub t, superscript t, is the thermal diffusion coefficient for species I. Lambda in the Fourier heat conduction term is the thermal conductivity, and J alpha I sub alpha I is the species diffusion flux. D alpha I that appears in the species diffusion velocity is the driving force for species I in each of the three directions as given by equation 13. The driving force involves thermodynamic forces that are generated by gradients in concentration, term 1 in equation 13, by gradients in pressure from the second term in equation 13, which is also referred to as the Barrow diffusion, and then due to any body forces such as a gravitational field or electrical field, which would be term 3. We typically neglect the body force term in this equation. Okay. So for the mass diffusion flux, the diagonal components of multi-component diffusion coefficient matrix are identically 0. And then also the diffusion fluxes and the driving forces for all of the species have to sum to 0 for continuity. And then the species diffusion velocities are often approximated, especially in our code, by mixture average diffusion coefficients, D sub mix, written in terms of binary diffusion coefficients, Dij, and the mixture composition, as given by equation 17, where the diffusion coefficients are symmetric and the diagonal elements are 0. We typically neglect Barrow diffusion term that I talked about earlier because they're typically negligible. And in most cases, we also neglect the Soray effect. However, sometimes in premixed flames, we do include it. And so you can simplify, finally, the diffusion velocity that is used for a mixture average formulation as written in equation 18. And then you can rewrite that equation in terms of mass fractions instead of mole fractions. And then the heat flux vector, which is in the energy equation, has 3 components representing diffusion of heat due to temperature gradients, it's Fick's law, the diffusion of heat due to mass diffusion, and the Dufour effect. And as I said earlier, we typically neglect the Dufour effect so that we are left with the heat flux vector that has the heat conduction term and the species mass diffusion term. So with this set of conservation equations and also boundary conditions, which are represented by characteristic waves, I'm not going to describe those here. We've written a code in my group called S3D. And it's a first principles compressible reactive Navier-Stokes code using higher order spatial discretization methods that are 8th order central differences in space and an explicit 6-stage 4th order accurate Runge-Kutta method to advance in time. We found that these methods are the most efficient to parallelize on supercomputers. I mean, there are other methods, spectral methods, as well as compact PAD-A finite difference schemes that require more complicated Thomas linear solvers that are more difficult to parallelize. So we ended up choosing an 8th order spatial and an explicit 4th order scheme for our code. The chemistry can be represented from over a range of complexities, from detailed chemistry models for hydrogen-oxygen systems, some of the simpler systems, to reduced chemistry. And as I said, transport model that we normally use is mixture averaged. The multi-physics capabilities that are in this code now, besides complex chemistry, we've added a Lagrangian particle tracking capability that's coupled with the Eulerian solver so that we can treat sprays, polydispersed, dispersed, dilute sprays, that is. So we're not treating atomization. And we have full coupling between mass, momentum, and energy between the different phases. We're also in the process of adding a thermal radiation model and starting to look at soot, coupling with the gas phase chemistry. This code has been ported to all of the major platforms that have evolved since the terascale age. So I guess it's now been about 25 years from teraflops or gigaflops, teraflops, petaflops, and we're headed towards exascale. So it's about 4 or 5 decades of scales. And this code, as I said earlier, has a particle tracking capability, and we've coupled now a lot of the analytics so they operate in situ as the solver is progressing. So for example, we can compute chemical explosive mode eigenanalysis on the fly, and we can also do anomaly detection algorithms, which I'll talk about tomorrow, on the fly to detect incipient occurrences of ignition or extinction, which then we can use to drive or steer adaptive I/O or adaptive mesh refinement or downstream analysis of those regions. So I've described the methods here. I should say also that we do apply a 10th order explicit filter to remove spurious numerical noise. So this would be comparable to de-aliasing at the highest wave numbers. And we resolve all of the spatial temporal scales, both the fluid dynamic scales as well as the thermochemical scales and acoustic scales. The boundary conditions are given by this reference by Poinsot and Lilly for Navier-Stokes characteristic non-reflecting boundaries for inflow, outflow, and also wall treatments. We can do isothermal or adiabatic walls. We also have a way to do permeable walls, so we can do mass transfer and energy transfer through the wall. For simple calculations like isotropic turbulence, we have periodicity instead of these NSCBC treatments. And we've recently also have internal boundaries by what we call multi-block code. So you can think of Lego blocks where you have various blocks of mesh grids that you can string together to create somewhat more complex geometry. So I'd like to show this plot that illustrates the degree of complexity with regards to chemistry and the scale of that. This is a plot that Ed Law and Tianfeng Liu generated some time ago. And it shows a plot of the number of elementary steps on a log scale. This is a log-log plot. Number of reactions versus number of species. And on this log-log plot, you can see the exponential growth in time. This is a little bit old because I think this was generated almost 10 years ago, but it does span about a decade of time. And you can see that hydrogen is somewhere here near the origin with about 10 species or so, 9 species, and small number of elementary steps. And then you go on up to methane and ethylene and some of the larger hydrocarbon fuels out here far away from the axes. Some of the primary reference fuel for gasoline, for example, PRF, N-heptane, diesel surrogate, and isooctane are out here. And so you can see that it seems to have a scaling of a factor of 5 between the number of elementary steps and the number of reactions. So they're linearly proportional, it would appear. Now, when you get out to like 1,000 species and 10,000 reactions, that's clearly not possible to include in CFD. So we have to reduce the mechanisms before they're amenable for use in CFD calculations. So we've worked closely in the past with Tianfeng Liu and Ed over the years. They've developed a systematic procedure for mechanism reduction and also for removing the chemical stiffness, the disparity in scales in time between chemistry and other processes, where their method starts with a detailed mechanism, for example, for ethylene with 70 species or N-heptane, C7H16 with 500 species. And then they apply this DRG or dimension reduction graph analysis that removes unimportant reactions and unimportant species, and they come up with a smaller skeletal mechanism that might be a half or a fifth the size of the detailed model. They then further apply timescale reduction and with quasi-steady state assumptions to come up with a reduced model that is far smaller. So for ethylene, they were able to get down to about 20 species, and for heptane, the reduction was even greater, so about a tenth of the number of species from the detailed model. So here it was about 50 to 60 species. And then for the transport, they do this thing called diffusive species bundling, which minimizes the number of diffusive species into smaller numbers of groups. And then lastly, they remove any kind of numerical stiffness on the fly in the DNS simulation so that we can use an explicit time marching scheme, which is much cheaper than any kind of implicit or semi-implicit method. And so in the end, we have a CFD mechanism that we can use that's 20 species, for example, for ethylene, and 60 species of that order for N-heptane. For parallelization of the code in a compressible fixed uniform mesh code, we kind of have a very simple domain decomposition. You basically take a large cube and you bust it up into smaller blocks. And for the longest time until recent appearance of heterogeneous machines that include accelerators, we used MPI only for message passing and for parallelism. When Intel came out with these mini-core machines, we started to use MPI for communication across nodes, and then OpenMP and multi-threading to deal with the mini-cores. For GPUs and accelerators, there are pragma or directive-based approaches, such as OpenACC or and other methods that allow you to go in there and annotate your code to send parts of your code over to the accelerator. And so in this simple decomposition of the domain, we have pretty nearly parallel load balancing, since all of the processors are working on the same intensity of work. They're doing kind of the same computation. So, and our communication, because we've picked a centered finite difference method, is almost entirely nearest neighbor. So we have ghost cells, in our case, that are about 4 mesh points wide for a 9-point stencil, that allow us to communicate on each face of the domain to its nearest neighbors for spatial derivative computations. And then we have parallel collectives for I/O. So when you want to write your information out and save it out to storage or to disk, and we might typically save about 200 to 500 restart files, which represents of the order, for the kinds of calculations we do, on the order of a few hundred terabytes of data for a simulation. So we can't afford to save more frequently than that, because the computer centers don't allow us to store more data than that. That's already a lot. And in these DNS codes that are represented by these large solutions of partial differential equations, the per node performance is not limited by throughput, but rather by memory bandwidth. That's because we have so many temporary intermediate variables, maybe 500 to 1,000 intermediate variables for a mechanism like PRF or N-heptane, that have to be and inner loops, through all the species, through all the reactions, that leads to a lot of memory traffic where you have to load all this information into the memory and into the registers, different layers of the memory, and then to use that information. And so that limits our performance in these CFD calculations to about between 5 to 15% of the peak floating point performance of a given machine. The code is extremely scalable and portable. And so in this plot here on the bottom right, I'm showing the weak scaling performance of S3D on now an older machine, Jaguar. And what's plotted is the throughput, or no, the cost per grid point per time step, or on the ordinate versus the number of processors. And back at that time, about 2010, we were up to running on of the order of 200,000 processors. And the flat line is indicative of the good scaling performance as you keep the problem size per piece of the domain constant, and you increase the number of processors, it's able to scale up to pretty much the full extent of the machine. And so, as I said, I guess I've kind of said this already, we get parallelism from data decomposing our 3D domain. So we get data parallelism, and each MPI process is in charge of a single piece of that domain. All of them have the same number of grid points and the same computational intensity. The only communication, interprocessor communication, is between nearest neighbors. I've said that already. The message sizes is large, so we accumulate a bunch of messages and send them off all at once, and then which is more efficient for communication than sending a bunch of small messages. And we only synchronize for computing the CFL or time step or for I/O very infrequently ahead of monitoring and synchronization. And those require all-to-all communications. Typically, the code structure, most of our CFD codes are written to be sequential, and they're bulk synchronous, meaning that you do a bunch of computations, as shown in this top left block here, and then you wait for the slowest member of those various processors to finish. So this is what they call MPI wait. And when that happens, then you move on to the next computation. And so it kind of proceeds computation and then wait for the slowest component. And that slowest component can be due to latencies on the machine or due to jitter on the machine, especially as you have larger and larger numbers of processors. All the processors don't all finish at the same time. And so the slowest one is going to limit the rate at which the rest of them proceed at. And okay, and then on the right here, I've kind of just shown you pictorially the mesh, the uniform mesh, and then the domain decomposition onto 4 processors with ghost cells in between. If you look at the communication cost to the computational cost, it's right now our communication is a small fraction of our computation, and it scales inversely with the number of mesh points that you put on a processor. And so our problem is not communication, but especially when you start to add more and more species for more complex chemistry, the work intensity increases, which makes the communication even less comparatively. This is a little bit into the weeds of the DNS solver, but basically in an explicit solver, you're advancing the set of primitive variables, that is the density, momentum, total energy, and species mass fractions on the left-hand side with an explicit Runge-Kutta method. And then on the right-hand side, you're constructing the various partitioned terms representing advection, diffusion, and chemical source terms. And then in an explicit our K method, we have 6 stages, intermediate stages for each time step. Gives us 4th order. And then a lot of the terms on the right-hand side that comprise diffusion, advection, and the source terms are written in terms of the primitive variables derived from the intermediate, the primitive variable vector. And so advection and diffusion types of terms and all of the governing equations require spatial gradients, and so you have to do spatial finite differencing and nearest neighbor ghost zone communication, whereas the source terms are pointwise functions, as well as the thermodynamics, the chemistry, and the molecular transport properties are also all pointwise functions of the solution vector, the species mass fractions, temperature, pressure, and so on. To give you an idea of the computational intensity of the chemistry, here we have a routine in our code that mimics the CK-WIP routine in Chemkin, and there's probably corresponding routines in Kintera and other favorite packages that you have. We've rewritten that and called it get rates in our code to make it more efficient. And so chemical rate is computed using an Arrhenius model. So for a simple global step model where A plus B goes to C plus D, the forward rate, reaction rate, is written in terms of a pre-exponential multiplier, C star, the concentrations of species A and B, multiplied by temperature raised to an exponent A, which is another parameter of the model, and then multiplied by the exponential of the ratio of the activation temperature to the temperature energy, or it could be either activation energy or activation temperature. And so there are, in the evaluation of the rates, there are lots of transcendental function evaluations which are very expensive to do computationally. The equilibrium constant gives us the reverse reaction rates, and then there are some additional terms that are required to be able to account for three-body efficiencies, collision efficiencies, and pressure corrections. And then for a given species that we transport, the source term for that species is then the sum of all the rates of all the elementary steps in which that species participates. And so that can be typically of the order of, I don't know, 5 to 10 reactions. I already said that the evaluation of the chemistry uses transcendental functions, exponential and log heavily. And to give you an idea of the number of reactions for a range of fuels that we've considered, from hydrogen, which has 9 species, 15 reactions, and to DME with about on the order of 30 species, heptane 52, and 16 species are in QSSA. 27 of those are stiff. For a primary reference fuel representing gasoline, detailed would have something like 861 reactions, 171 species, and we can get that down to about 116 species with about 55 species put into quasi-steady state and stiffness removal of about 93. And so that gives you an idea of the scale of what is feasible today in these CFD calculations. So obviously we have a need for high-performance computing to resolve all the chemistry and the species as well as the fluid mechanics. And so that kind of brings me to this slide that shows how DNS has kept up with growth in HPC, or Moore's law, which basically says that the number of transistors doubles about once every year and a half to 2 years. So we've been able to get to larger, faster computing power, and this exponential growth of both computing as well as CFD, as shown in this plot. We're basically plotting on a semi-log plot, the computational problem size, which is given by the number of mesh points multiplied by the number of variables. So in combustion case, that's mostly the number of chemical species that you're transporting plus 5 other variables. That has gone up since 1995. We were looking at about 1 million degrees of freedom to recently where we're looking at about 2 times 10 to the 11 degrees of freedom. And so it's grown immensely over about 2.5 decades. And with that growth, we've been able to represent much more realistic simulations, where early in the mid-90s, people were doing DNS in 2 dimensions, so that would be not realistic for the turbulence. Or you were doing 3D DNS, but with 1 global step or infinitely fast chemistry. And then in time, we were able to start adding complex chemistry, but still restricted to 2D. And then we started in about the mid-2000s to add, to actually look at 3D turbulent flows coupled with moderately complex chemistry for hydrogen, syngas, and methane in very simple configurations like slot jets and temporally evolving shear layers. And then most recently, we've been pushing up in pressure and also simulating smallish laboratory scale flames and comparing with experiments directly. And so now we are able to look at things like fuels like endodecane and various other jet fuels that are reduced down to about 30 to 100 some odd species in domain sizes that are a couple of centimeters at ambient pressures and still the order of several millimeters at very high pressures at 60 bar, for example, and start to look at the detailed, intricate coupling between turbulence and chemistry. As I said, the DOE and the US, at least under the Obama administration, has developed this program called National Strategic Computing Initiative. And DOE was a prominent agency as part of that initiative. And they've deployed machines for open science at both Oak Ridge as well as at Argonne. And the current machine that's deployed at Oak Ridge is called Summit. It's 200 petaflops. And then through an open competitive allocation process that DOE administers, users from academia, from labs and industry are able to apply for computing cycles. And that's done on an annual basis. And you get awards that are of substantial amounts of computing time of the upwards of 100 million hours per year once you show that your code can scale and utilize these resources. And so with that kind of computing power, it is possible to do small laboratory scale flames. This is a hydrogen air lifted jet flame that we simulated a couple years ago. And you can get insights into all kinds of physics from lifted flame stabilization to auto-ignition. And the data from the DNS is being used by groups from around the world to look at validation and ideas for developing RANS and LES models, closures. It's also possible using these massive computers to do very detailed large eddy simulation. And this is an example from Thierry Poinceau's group at Surfax, where they've simulated the light around problem for ignition in a full annular combustion chamber for a helicopter developed by Turbomeca. Okay, and so from this kind of DNS work, a number of benchmarks equivalent to the laboratory experimental benchmarks are being developed in shear layer configurations to look at extinction, local extinction reignition processes, to turbulent Bunsen and turbulent jet flames with and without pilots, to looking at homogeneous charge, compression ignition types of problems with DME and with PRF for relevant to engines, and looking at lifted flame stabilization, both in non-heated as well as in heated vitiated co-flows, looking at how they're stabilized, for example, in a diesel engine, to looking at fuel injection processes, for example, in a jet and cross flow, in a transverse flow. So you can imagine injecting fuel into a relatively hot cross stream of turbulent air or vitiated products mixed with air, and watching how the flame stabilizes in this jet and cross flow, either hydrodynamically behind this low velocity region, or through an edge flame, or through autoignition if the cross-stream temperature is high enough. We've also started to look at flame wall interactions, and especially looking at heat transfer, heat fluxes near the wall, as well as what happens in this low velocity boundary layer near the wall if the flame, such as hydrogen, which is highly reactive, propagates upstream into the injector. And so we can look at flashback, for example, with hydrogen, and the coupling between the flame-generated dilatation and the boundary layer structures, these hairpin-like structures that couple so that you can actually get negative velocities that cause the flame to move even faster in certain regions near the boundary layer. So let me then go on. Let's see, what time is it? It's 3:45. So I should probably go on to the next part. Let's see, maybe we should take another 5-minute quick break, and then I'll pull up the next part of the talk. Okay?